So first of all, just as a small introduction, I think that Simone has already told you that about the organizations of the next two lectures, but just in case you missed it and you wonder what I'm doing here. So this lecture and the next one will be held by teaching assistants. So you may know some of us already from our Discord server, where we answer our questions about homeworks and exercises. And yes, so this lecture will be held in the first part by me and then by my colleague Sai. And the lecture next week will be held by another teaching assistant, Saleh. And so, as a short introduction, I am Marina, and I am in my fourth semester of the AI/ML studies, and I did this course last semester. And yeah, now I'm here. Yes, we have a bit of problems with recording, so I present here, but we record on another laptop, but we hope that we will not have any problems and you will be able to watch it at home. All right, so just maybe as a quick start, so in the next two lectures, they are about very kind of similar topics, and we will talk about some different extensions of LLMs. So once we have a decent base model, then what kind of interesting new developments are there that can make them either better or faster? So we will look at many recent developments in this field. And so first, just as a short recap from the last week. So what did you learn? You learned about different types of transformer-based architectures, such as encoder-decoder and decoder-only and encoder-only models. And you also learned about zero, one, and few-shot learning, and learned what prompting is, and different types of it, such as continuous, discrete prompts, and in-context learning. And then you covered some problems of LLMs in general, and specifically, for instance, with respect to hallucinations and what that means. And so now in this lecture, what we will do is, first of all, my part, I will talk about some of these contemporary developments. So once we have our base model, first, how can we train it? How can we continue the training to make the model even better? And then what can we do during the inference to improve the performance even further? And after that, my colleague will tell you about reasoning and efficient training and inference. And by the way, if something is, if you have any questions, if I am too fast or too slow, then please just let me know. So in general, very roughly, you have these three stages of LLM training: pre-training, fine-tuning, and alignment. And the first one is what you are probably already most familiar with, pre-training, where, just as a recap, you have a huge corpora with text that you scrap from pretty much everything you can find. So all the papers, articles, books, and whatnot, and you put it all through the LLM. And as a result, it learns this kind of basic language modeling. So it learns what words are likely to follow after one another, what's some basic grammar of languages. And after that, it is already quite good in mimicking human text. But we don't want to stop there because we want the model to perform some specific tasks. And for that, we use the second training stage, which is fine-tuning, where we have, in general, some smaller data sets in maybe a few specific domains. And then we want the model to, to learn how to do these actual tasks. And here, so how does this exactly work and what types of fine-tuning do we have? So here is an example, a screenshot from the Meta Llama Hugging Face account. And you can see that there are really a lot of different models that sound pretty much the same, but also not really. So you have this Meta Llama 3 billion, and then the same, but with Instruct. And then you have a chat models as well. So what is the difference between all of them? So what is it even? And so here we'd like to introduce two different concepts. And the first one is that you're probably already most familiar with, which is just standard supervised fine-tuning. And this is just how you would imagine fine-tuning in its classic form. So you want the model to learn how to perform a specific task. Maybe you have a smaller data set in either one domain or some very similar domains. And then you want the model to learn to map from the input to the output. And so, therefore, you can have a pretty much specialized model in one area, but if you especially build some large applications such as ChatGPT, for instance, then you don't necessarily want the model to be only good in, let's say, text translation. You want it to really have this kind of general ability to perform any instructions that the users tell them. And so this is the idea of the instruction tuning. So here, instead of having only data from one specific domain or a couple ones, you rather focus on the model's general ability to interpret instructions. So besides input and output pairs, you also have this task description, and there the model's main goal is to learn how to interpret these task descriptions, and then based on them, perform this task that the user asked them to. And then the idea is that it learns this interpretation, and then during the inference, it may also be able to transfer it to some new instructions that the user asked them to do. And here, in this below, you can see an example of Flan, which is the first framework that introduced this instruction tuning. And you can see here examples, for instance, please translate I love you to French. So you have this instruction, please translate to French, and then you have this I love you, or read and answer the question. So you really not only have, for instance, a text and translation, but you also tell the model what it needs to do. And yeah, then you just put a bunch of such examples into it, and then it actually learns this general interpretation. And so it can perform multiple different tasks. Okay, so yes, now the model can do has this kind of instruction tuning ability, but are we done? So is our model now finally good? So probably not, because there are still some problems. So in both pre-training and fine-tuning, we of course use a bunch of data. And it is often impossible for humans that develop this model to go through all of this data and look at, okay, do I want to have now a training corpus? What don't I want to do? You just pick, okay, all the Reddit posts that I can find, they all go there. But what can happen is that there may be some biases in this data. And you may first think about some cultural biases, which also can be the case, so that maybe the model learns some jokes or wrong representations about some population groups, but not necessarily. So you can also have something like language biases, where, for instance, the model, there were too many old texts in the training data, so the model learned language that is not really used anymore, or maybe vice versa. It had a lot of conversation and then it generated just brain rot, but it's not how we want to converse with it. And the second point is that a model actually can even generate correct answers and score maybe high on some benchmarks. So even if you have something like a QA benchmark, and then the model, let's say, answer questions about popular science, then it can generate really eloquent, really nice answers, scientifically formulated. But if you are really just general user, then it may be too complicated for you. So the model will score really high, but it does not necessarily mean that it is what we human want our output to look like. And so all these problems can be solved with alignment, which is the last phase of the training, where the idea is to incorporate some human feedback into this training loop and to align the model with our human preferences. And yes, so basically you just have some people and you ask them, okay, do you like this text or not? And then based on this feedback, you train the model. And now we'll look at it at a bit more detail using with two different algorithms. And the first one is reinforcement learning from human feedback. And this is probably the most popular one. And this was introduced in the GPT-3 paper. And since then, many really big models, so Claude, Gemini, also other GPT models, they were all trained with RLHF. And just very general, because before we go into detail, so you have a reward model that tries to predict how good an answer is. And then using this force that the model generates, you train your actual language model. And so now how does it work exactly? So first, of course, you need to have a model that is already quite decent, so it already understands how language works. And then you collect a set of inputs. And for each of these inputs, you generate a bunch of different outputs. And then you ask humans, okay, so here is my questions, here are all the outputs, how do you like them? And so for each output, the model generates a scalar score so that all the answers are ranked. So let's say the best answer receives 1.0, the second best 0.9, etc. So then you have these triplets of input, output, and score. And with that, you can train a reward model so that based on this data, it learns to predict the scores. And how does such a reward model look like? So it has to be an LLM because it has to interpret human language, but it also has to make these predictions, these score predictions. So you can basically just put either a classifier or a regressor head on top of the model so that it returns a score, depending on how you want your score to look like. It may be just a class or a continuous value. And yeah, after that, so you have your reward model, and the next goal is to train your actual LLM. And what you do is you first make a copy of your original model, and this will become important later. So now you have two of them, and they look the same, and you start training them. You start training one of them, and you fine-tune it using a reinforcement learning algorithm, which is called PPO. And there is a separate lecture that explains how reinforcement learning works in detail, also with this algorithm, so we will not go into that much detail. But what is important to understand is that roughly it has two main components in the loss function of this type of training. So first of all, of course, you want to generate output that produces good rewards by the reward model. So you want to maximize the probability of the outputs that have high reward. So yes.
The reward model only get the answer or also the prompt?
It gets the prompt and the answer. So that yes, so that exactly it. Because if it only would get the outputs, then it would not have the context, right? Because based on what question you ask, many different answers can be better or worse.
And it wasn't there even for one app.
Ah, yeah, okay. No, it's always input, output, and then the score produces. Yes. So, okay, so now you have this reward model output. Is it enough? No, because if we just let us take a look on this example. And this one is actually very popular. You may have already seen it. But basically, there is this kind of game where you have to steer a boat and collect money on this kind of track. And the more money you get, these are these yellow circles, the more scores you get. And so the idea, right, is just to follow this, this trail. But what happens is not really what you want to expect, right? So it just runs in circles. And if you look in the corner in the bottom left, then the score is actually gets even, it gets always bigger and bigger. And oops. And so what happened? So why does it perform so weird? Is because of a thing, let's say, called reward taking, where basically it can be possible that your reward model is not perfect, that it learned for some reason to give really high scores to outputs that are not necessarily that good. So for some reason, it decides to, if we translate it on the language, that if you generate this one specific word, then it should just give highest score. And so what happens is that this agent, so your LLM, will exploit these flaws and always receive high scores without genuinely learning the actual task. And so now how can we prevent it? So the idea is that if reward hacking happens, it means that probably the model, let's say, just generates one word, and so the probability distribution of the output will also significantly change, right? Because it's still, if it's good, then it still has to have this kind of pattern that will mirror how we humans, what words are more likely to come after one another. But if there is reward taking, then the model just cannot do it anymore. And so what we want to do is exactly why we copied this model a few slides back. So we want to make sure that this model still does not deviate too much from its original version. And this is why we need scale divergence. So this is basically a measure of how one probability distribution is, how close it is to another one. And what we do is we add this term as to the loss, so that we see that if this divergence is too big, it means that the model deviates too much from its original capabilities, so we want to penalize it. Yes, and this is how RLHF works. So you have this kind of trade-off. Yeah, so do you have any questions so far? All right. If not, then we will continue. So yeah, reinforcement learning. So this RLHF sounds really nice. And as I said, many good models were trained with that, but it still have some kind of problems. And in general, the setup can be quite tricky and costly because RLHF uses what's called, it's an example of online reinforcement learning, where the environment changes with the action of the agents. And what it means is that your input or kind of the state, it's always changes depending on what your model will output, right? Because the output will basically go back to the input. And so it's so what the model generates is directly relevant to what will come next. And this kind of setup is really hard to get right compared to when you already have this kind of static data, you know that nothing will change, and you can just train it based on that. And furthermore, you have this explicit reward model. So you have your original language model and also an additional reward model, which is, first of all, just an additional engineering step. So if your reward model is bad, then your LLM will also be bad because it will just produce bad scores. And you have to train two models, right? So all the costs, all the time for alignment just is multiplied by 2, basically. And so then people thought, okay, what if we don't even need reinforcement learning? What if we can find a way to incorporate these preferences directly into the training of our original model? And this is exactly what DPO, or direct preference optimization, is for. So yes, they basically construct the loss of our original LLM in a way that these preferences are built into this loss implicitly. And so how does it work? And by the way, we have the formula on the right. You don't have to know it. So you have to know these general steps of how it works, but we will not ask you to write this formula in detail. So don't worry about that. This is just for like additional explanation. Yeah, and so what steps are there? So first is the same as for RLHF. Of course, you have to have a disc model in the beginning. And then you collect also a set of prompts. And for each prompt, now you generate only 2 outputs. And then you ask humans to, okay, here is my input, here are 2 answers. Which ones do you find better, and which one you find better, which one is worse? And then you have these triplets. So you have an input, you have the chosen output, and you have the rejected output. And now you want to train the model, right? So you also do a copy of it for exactly the same reasons that described previously. And then you want to do what's called optimized relative log probability ratio against the pre-trained model. So what it means is that you basically want to maximize the probability of the chosen reward, so this term on the left, while minimizing the probability of the rejected reward. And but you also, of course, don't want your model to deviate too much from original capabilities. So you normalize this by this P reference, which is our reference policy, our reference model. So by that, you also ensure that the model stays close to what it originally are. Yes, this is how DPO works. So sounds like a nice alternative. And also a couple of models were trained with that. So Llama is the biggest example, but also others like Gemma or Xtra also have used it for the training. But it also has some problems. So first of all, you have this binary accept or reject decision. So you have only, okay, this output is better and this output is worse. But this is not necessarily something that you can describe the many things in the world with, right? Because maybe you have 2 outputs and they are both kind of good, and the other one is a little bit worse, right? But in this setting, you are then obliged to penalize the worst one as just rejected. And also, if you want to have multiple outputs for the same input, just because you want to have a bit more kind of different samples, then you have to do this exponential comparison because you have to have always these pairs of 2, and of course, it just explodes. And furthermore, the scale divergence, so this difference of the 2 distributions, is kind of more implicit here because you don't have this explicit term that you substitute, but rather you normalize by this probability of your reference. But this is not, let's say, not as explicit as in RLHF. And so what can happen, and what also some research papers point out at, is that as a result, you have more chance to have reward taking, so that something goes wrong. And so yes, what performs better, RLHF or DPO? People are not really aligned on that. So some experiments say that RLHF is better, some say that DPO is better. I think that a little bit more tend to say that RLHF is better because it can kind of grasp a bit more complex comparisons. Yeah, but in general, it really depends on what problem you have and how many resources you have, because DPO is also just a bit simpler to get to work. Yes, and so this is basically, these are the two algorithms with which you can do this alignment phase. So if you have any questions, feel free to ask.
Are there any methods that process the models output partially, saying this part was good, but I didn't like this part? But instead of just rejecting or giving a bad word to hold on to the partials or make anything.
I don't know about that. I know that RLHF can be done a little bit differently, so that as far as I know, you can also, what a bit of improvement is that you can evaluate different outputs kind of jointly, so that you compare more outputs to each other, so that you have kind of broader samples. So there are some improvements, but I don't know about this one, so I can't answer this. Okay. Yes.
So the direct preference optimization, we are just affecting the logs that the model logs, not having any additional critic network. But we are still kind of doing both of them, just blind, basically.
Yes, exactly. So here we just modify the loss of this LLM, and so we don't need any reward model because we just directly train it. All right, I think then we can continue. So now we finally have hopefully decent model if we do everything correctly. But are there still any issues with our resulting model? Maybe because LLMs have some inherent problems. And how can we extend them even further during the inference so that the quality of the output is even better? And so for this discussion, we can look at two different questions about which we can just think whether the LLMs have to answer them correct, right after the training. So the first one is, when was TU Darmstadt founded? So is it some kind of general knowledge that every model has to know, that everyone has to know? So this is probably up to debate, and some people can say yes, some people say no. But for example, if I ask a model, who am I? So who is Marina Sakharova? I am not as influential, famous person, so probably the model does not have to know, for example, about me, right? So first of all, there is this point that, yes, there are just many things in the world that is world's knowledge, but not necessarily that relevant, that if you would to just put all these smaller things into the model training, then just probably would be too much. It does not have to remember that. But also we have things called curse of the knowledge cutoff, because as the world continues to exist, its knowledge also just gets constantly updating, because there are more and more papers get published every minute, and some books get published, or some articles on the internet. So just this knowledge just keeps constantly expanding. And if we would like our model to keep up to date with it, then we would just have to never stop our training. And this is just not feasible, right? We cannot train our model forever. And then the second question is, do language models have to be good at math, right? Because the fundamental idea of transformers architecture is that it is designed to be good at textual tasks, but not necessarily as a math. So do we have to maybe fundamentally change this architecture so that then it is some kind of math genius? And now we will look at a few examples that can help us fix these problems, that can give LLMs access to either some information retrieval or to some kind of tools. And so the first one that can help us to solve our first problem, so not having some information, is retrieval augmented generation, or RAG. And this is actually pretty much an umbrella term, and it can mean really many things depending on what application you have. But in general, it is a term for some kind of additional information retrieval. And information retrieval is that you need to find material of unstructured nature, so basically text usually, that satisfies your information need from within large collections. So you have a lot of documents and you want to find most relevant ones. And yes, this can occur in many different forms. So if you have, for example, a code generating LLM, then maybe you want to give it access to your repository. Or maybe if you have some kind of tool that helps you query your documentation of your company, then you want to put the documentation into vector database. Or you want a fact checker, then you can give it access, API access to Semantic Scholar or ACL Anthology or Archive or whatever. Yes, but first of all, just in general, how does this whole setup looks like? And we will look at in more detail in a minute, but for now, what we have in RAC is some kind of software that connects the user, the LLM, and some kind of external sources. And so then when the user sends a query, then the software searches these external sources that can be anything, right, as we discussed earlier, and returns the most relevant information for this question. And so now it has this kind of enhanced context, and it creates a prompt with the user query, with this context, and sends it all to the model. And now the model hopefully is able to find the correct answer. And so now how does it work maybe more specifically? So here we can look at the example of LangChain. Actually, there are also many different tools to do that, but here and these tools also work in very similar ways. But here we kind of want to work with LangChain because, first of all, this is one of the most famous and first tools to do that, but also because you will do some things with LangChain in the homework 4. And so now we want to kind of show you what it does on a high level. So first of all, of course, to extract information, you need something to extract the information from, right? So you need some kind of a knowledge base. And to construct this knowledge base, it can be in many different forms, but now we want to show you how vector stores work. So vector stores are basically just databases that store and manage vector embeddings. So instead of having, let's say, this structural data with all these rows and columns, you can have different vectors, and then to find something, you embed your query, and then based on some vector similarity, it returns you the most relevant entries. And yeah, so how do you create such a vector store? You collect relevant documents, and then you split them into small pieces called chunks that can be then individually retrieved. Because if you have, let's say, a whole book on, I don't know, cybersecurity, and you want to know about jailbreaking, that not the whole book is going to be relevant. Probably only a couple of pages or even a couple of snippets. And so you don't want to retrieve the whole book, right? Only the most relevant parts. So you split it, and then you create embeddings of these chunks, and you put them into this vector store. And so now your knowledge base is finished, and you can start working with the software. And now, let's say a user asks a question, so what is RLHF? And of course, nowadays it is quite a known term, so this model would probably know it, but just for the sake of example, let's say that it does not. And so we perform this kind of semantic search. So we retrieve the most relevant documents based on some kind of similarity metric. And the most popular and just intuitive one is cosine similarity, of course, but you can also do some more interesting things, such as maximal marginal relevance. Because one problem with cosine similarity is just that it can output documents that are all pretty much similar. So if you retrieve 2 documents or 10, then it does not really introduce any new information, just because the information that you found there is really, really similar. And so MMR tries to kind of solve this problem. So it tries to find the snippets that are most similar to your query, but at the same time, also the most different to everything that you retrieved before, so that your whole output is kind of more diverse, and the model can learn more different information. Yeah, so then you have retrieved your documents, and then you can also additionally filter them. So you can have something like only please return K first outputs, or maybe similarity threshold. So if cosine similarity is smaller than 0.8, then don't output it. Yeah, and yes, then you just pass it to the model, and the model generates now hopefully a correct answer. And this kind of setting is useful, especially if you have, let's say, static or like semi-static data, so something that does not change that often, right? Because if you have, let's say, also a book, then it is not really to expect that a next version will come every few minutes, right? But if you have something like a weather forecast, then of course it's something very dynamical that can change every time. So something like that does not make sense to put in such a knowledge base. Yes, so this is pretty much how RAG works. So now, did we solve our first problem completely? Can we just do everything and extract all the data? Not really, because first of all, there are still these tasks where we don't even need to retrieve information. So for the math, I mean, of course, you theoretically can try to create a database with all the possible math examples in the world, but this is just not going to happen, right? And also, when we solve a math exercise, we want the model to have this, we want to have this kind of computational process and not just extract the answer from somewhere. But also, there can be many problems that do not require only one knowledge base. So if you have something like code completion, then maybe you have a bug that has something to do with your repository. And then you have to provide the model access to your code. But maybe you have a bug that has to do something with an external library. And then you, for example, want to search Stack Overflow. Or you want to have a new functionality, but don't know what method to use, so you query a documentation. Right? And as a last point, it is, yeah, so you have a question?
What do you use so for math? It is unnecessary to use RAG because there can be all math problems. But does it hurt to still do RAG for math questions?
So maybe you can do that, but actually in a minute we will take a look at a bit better solution, because instead of yes, we will talk about it in a minute. It's actually on the next slide. Yeah. So okay. And then as a last example, okay, we can use similarity, but not always just similarity can play a role. So for example, if you have scientific research, then what are even papers that you want to have? So are these papers that are most popular and have highest citation counts, or maybe something that has the newest results, regardless of whether it's published somewhere or has more citations, or does it have to be peer-reviewed? So it really can be different and not just, okay, we have high similarity, then we should retrieve this. And what we can do to fix some of these problems and improve it are to define some kind of tools that the AI can learn how to use them, right? And so here we come to the term of AI agents. And so originally it came from reinforcement learning because, because you also have this kind of setup where you have an environment and the agent does not really know what's best to them, but it tries to kind of explore and find the best solution to the problem. But nowadays, it is actually a really, really overloaded term. So like everyone has some kind of fancy agentic AI tools. And so anyone basically calls anything AI agents. But just so that we are on the same page and know what it means, so we will define AI agents as AI systems that can set or interpret goals, plan actions, use some tools, and make decisions based on feedback and adapt to complete tasks. And now we will look at what exactly it means. So what is using tools or making decisions? And here we also just, let's take LangChain and continue with this example and look at a bit more details. So now we have, let's say, our travel buddy that helps us to plan our next trip. So it has access to, for example, some API, weather.com API, or it can generate you some sites. It can retrieve some popular sites. So basically what you do as a developer of such a tool is that you redefine some functions. And for example, this get weather can connect to this API, right? Or to get sites, or for example, in a math task, then it can have something like function for multiplication or function for just anything basically that can be automatically computed. And so then the user asks a question. For example, how is air humidity in Lisbon now? And then the LangChain collects all these tools that you have pre-implemented and puts this all into a system prompt. So it says, okay, here is the user query, and you can use these tools to answer this. And you should also use a certain format, because often we have some parameters, right, with which we want to call the function. And so the model has to know how to construct this tool calling. And what happens then? The model uses reasoning, and my colleague will tell you about reasoning in a while, but basically it is just like an internal thinking process where the model decides, okay, what do I have to call? What do I even have to call any? And then it returns this call of a tool, and then LangChain executes it and returns the output to the model. So here, quite simple. Of course, you need get weather to find humidity, and it outputs probably a bunch of data. So what temperature is, humidity, wind, how fast it is, etc. And now there are two possibilities. So either the answer is already found, and here it's very simple example. So of course it has now everything to answer, and now it just combines the original user query and the information that it found and generates the output. But maybe you have some more difficult task where you have, let's say, multiple tools, or maybe you use the some wrong parameter to call the function, and then the model just iterates and goes over and over for a couple of iterations until it finally finds this correct tool and parameter that it has to call. Yes, and so this is pretty much how this agentic setup works, and you can use it to extend your LLMs in quite many different powerful ways. So does it mean that now finally we can do anything with AI because now they have access to such tools? So also not really, because first of all, currently these abilities are limited by our pre-implemented functions, right? So it doesn't matter how good our agent is, if there is no function to execute, if there is no tool, then the agent cannot execute this tool, right? And you have to always think about, okay, what can I add? You have to implement that, make sure that it works. So it is still not this kind of maybe AGI, but rather you always have to always think as a developer. And it's still quite limited. And then hallucinations, it's of course access to external information allows to reduce hallucinations, but it does not mean that it gets rid of them completely. Because first of all, of course, the agent is not guaranteed to select the correct tools, select the correct parameters, to interpret the output in the correct ways. So anywhere there can happen some mistakes. But even if the agent does everything correctly and it's perfect, then still the retrieved information is not necessarily correct. Also because of the reasons that we discussed previously, right? So what if the information is outdated for some reason? A cosine similarity just does not work for our case. And just maybe as a last concluding example, also one problem, maybe not from the perspective of this technology, but rather from human perspective, is that many people tend to rely on AI tools more and more. So now you can see even more headlines where companies use vibe coding, so that where AI generate. Yeah.
So is this just pure from system code, or is there something failing what to use and etc.?
No, this is in the LangChain specifically, and also in these frameworks, everything happens in the inference. However, there are also some newer models that also were trained to select these tools.
Also, since now models can basically program 10 models, it's like quite or something, their outputs, and then therefore not be limited by a set of tools that they use.
On the one hand, it can. On the other hand, we then also come to the third problem, right? Because if we allow the model to just generate all these tools by itself, then how can we as humans be sure that it really works correctly, that what it's implemented actually works? So of course, we can make it automatically like that, but even in this case, you need some kind of human input to be able to just, yes, make sure that it does not, as here in this example, deletes your whole production database, right? Yes, and so basically this is pretty much this last point that, of course, you can automate many things with AI, and this is also what more and more companies do. But of course, if you do not have any person who is experienced in programming and doesn't look over what AI does, and especially give it access to some production software, then of course things like that can happen. And yeah, so this is pretty much the conclusion that of course these things can significantly improve what you can do, but yeah, you still have to be really careful and verify everything that these tools do. Yes, so here we actually come to the quiz, but before, do you have any questions?
Cool. And for people who came late and wondering what's going on in this class, I'm Sai and my colleague Marina. We are two of the teaching assistants and we are taking over today's class instead of Simone. And I will be taking over the rest of the lecture where I'll be talking about two of my favorite topics. One is logical reasoning in LLMs, and the other one is how to efficiently train, fine-tune, and infer from these models. So even before I start, I want you to answer something, or maybe if you're not answering, I want you to at least think to yourself. We all know that LLMs are just autoregressive mathematical models. I mean, they're more than that, but that's the base. And what they do best is try to find the next most possible word and try to find a way to complete a sentence. But that's not all that we use LLMs for. We use them for everything from coding to helping with your homeworks, which please don't do that, and or asking advices for important life decisions. How can a mathematical model that's just autoregressive do all of this? How can it have the capacity, the cerebral capacity to think about these things logically and have the set of facts and infer logic from that? And how can it actually reason? To explain what I mean, I have an example here. This is something that traumatized a lot of people a couple of months ago. Imagine you ask ChatGPT something like, I have a car and I want my car to be washed, and the car wash is like 100 meters away or 200 meters away. Which is best? Should I walk to the car wash or should I just drive my car? And 9 out of 10 times, ChatGPT would directly tell you to walk. And it's even giving you like a lot of reasons why it's good to walk. And because 100 meters is barely enough to even warm the engine up, and it adds unnecessary things and it's bad for the environment. So you should probably just walk, which is stupid. And I said 9 out of 10 because I've tried it like 100 times yet. And it is stupid. Even someone who is not the brightest peer in the farm could tell you that you have to actually take your car to the car wash if you want it to washed. But a model that's trained on so much data that's coming from such a huge vendor does something that's a mistake in something that's so trivial for us. Why is that? And why is it failing to logically reason? And what is logical reasoning in the first place? So, reasoning can be defined in one of the very early papers discussing it as a phenomenon or process where you give an LLM a set of finite facts or evidences. The LLM takes these facts and it might have like previous experiences. So it takes all of this that it has and tries to somehow infer a decision or try to reach a conclusion that's new. That is what we call logical reasoning. And it's different from what we've already seen. It's not just retrieval, because retrieval can give you with all the facts that you want. But imagine you have to get something that is not given these facts. You have to know how to manipulate these facts and how to formulate them in a way that you can infer something that's new, that's not given. And it's obviously not just pattern matching, because in this example, it barely just pattern matched that, okay, this is a short distance and short distance equates walking, which is better. So it just pattern matched it and did not really think through it. It has to know when to break a pattern that it sees. It's probably seen this pattern a lot of times when it was training, and it just blindly relied on that instead of relying on actual reasoning. And also, it's not just generation, because trying to find the next most probable word doesn't have anything to do with knowing if it's the correct, or I mean, knowing it's the correct reasoning behind why we chose that word. And why do we even care about all this? We know that LLMs are really, really good at pattern matching, and that's probably how they can solve a lot of the tasks that they're doing. But this is not enough if we want true reasoning. And this is not enough if we want to really extend or really push it beyond what it's trivially just used for. And if it was just doing pattern matching, then ChatGPT would be bankrupt by now. So, how can we how can we induce this kind of reasoning? One famous method to do that is chain of thought prompting. You might be really, you might be familiar with this term from previous lectures, or you might have uh, known it from Instagram Reels, like I did. So, standard prompting would just give you, would just give the model a set of questions and the answers, and ask the model a new question, and the model is trying to mimic it and give you an answer. Chain of thought prompting, on the other hand, it's not just giving the model a question and an answer, but also breaking down the answer and breaking down the whole task in hand, and also telling the LLM how you arrived at this answer. So instead of just giving it a scenario and asking how many tennis balls does this guy have, you, instead of just giving it the answer, that the answer is 11, you also break it down saying that he has 5 already and he has like 2 extra cans, these cans have blah blah blah, and then you add this, you get 11. And then when you give it a new question, the LLM is trying to mimic the same style of answering that you gave, and it's also trying to break down the question that it has in its hand, and trying to arrive at a conclusion, which turns out to be correct in a lot of cases. Any doubts on this? Good. So, since chain of thought prompting is also a prompting technique I hope you guys remember few shot and zero shot prompting from previous lectures. If you don't remember, I hope you answered it wrong in the quiz as well. Few shot, since it's also a prompting technique, we can extend the same concepts to chain of thought as well. So zero shot chain of thought is not giving it any examples per se, but just telling it to think about it step by step or something like that, or think about it deeply step by step before you answer or something like that. You append a universal tagline to your actual prompt, and you're just prompting it to think step by step instead of showing it how to think step by step. And few shot prompting is going one step further, not just asking it to think step by step, but that's a mouthful. Asking it to think step by step, but also showing it how to think and showing it how to break down a specific task. For example, you can, I hope you've seen this, whatever. I hope you've seen this picture a lot of times. In normal zero shot prompting, you just put half of the answer and hope the model finishes it. And instead of that, in zero shot COT, you don't give half the answer, but append the universal term, and it's trying to do it. And in few shot prompting, instead of just giving the answer, you are also giving how to break down and get the answer, as we saw on the previous slides. So this is a good approach. Does it work? Turns out it does. This and the previous car wash test was done in the span of like 5 minutes in different conversations, and I copy pasted the same prompt but just added think about it step by step before answering. And right now the model says you have to drive the car there, and it gives you proper reasoning as to why you have to drive it there. And the second time I tried, it was even sarcastic and said like, unless you can carry your car in your hand, there's no way you could drive. There's no way you could walk there or something like that. So just adding one extra tagline can put a massive difference in how it's answering. Any yes?
So I know now the models are instruction tuned, so they see after the journal you don't need to get a lot of these kind of parameters. So does this chain of thought happen also when they're not instruction tuned and when they're just working?
It is similar, but chain of thought prompting was invented first before instruction tuning came. So this is not chronologically in the order of how they were invented. Chain of thought was already there, and then it was kind of extended into instruction tuning. Any other questions? Good. So now we have proof. I mean, we cannot really call it proof, but now you can see that it's working. And you can actually take it one step further. We know that chain of thought prompting is taking one specific thought process, which is called chain of thought trail. It's taking one trail and trying to get an answer. But what if that trail is wrong? It is still an autoregressive process. What if the trail is wrong? And what if the thought process is wrong? And the thought process is, if the thought process is wrong, the answer might also be wrong. So how can we fix that? Instead of taking one trail, we take multiple trails, multiple thought processes, which is done by prompting it again and again, where you take multiple thought processes, and each thought process would probably give you a different answer, and then you take the majority of it, which is called self-consistency. So As you can see in this example, you give this, you prompt the model again and again, and then each time the model is giving you a different answer. I hope. Okay. Each time the model is giving you a different answer, and you take a majority of, you take whichever answer is the majority. And how do we get this diversity? Because you're just prompting it again and again. What if it gives you the same answer? You need some diversity in how it thinks. You need different thought process. That can be achieved by changing the temperature. I hope everyone knows what temperature is. Please tell me you do. Okay, in case you don't, temperature is the hyperparameter that's baked into the softmax function, where if you increase the temperature, it kind of levels up the probability ranking. So it is possible that something that's slightly less possible is selected instead of the most possible one. So by increasing temperature, you are making the model more creative and making it think in, yeah.
Sorry, could interrupt.
Yeah,
Are
yeah.
you also interested in the reasoning path or only the result? Because would it also be possible, or on the percent consistency, do we like choose one reasoning path with the answer afterwards? Okay.
No, in self-consistency, we are only focused on the answers because it is possible that you are getting the same right answer through multiple different reasonings as well.
Yeah, because also all the reasonings path might be just wrong, but
Yes, it's possible, and we will be discussing about that in like 5 slides later. But you could call me again when we get to that part. It's true that it's possible that the chain of thought trail is wrong, but still gets a right answer. But the basic intuition is that if you are getting the same right answer through multiple various ways of thinking, it's probably the right answer. That's the intuition behind it. So, and we know what temperature is. It increases the randomness in the model's output, the randomness in how it thinks. And through that, we can arrive at different ways of different chain of thought. And then we take the majority answer that it gives. Any questions? Good. So, doesn't mean we've cracked it. Doesn't mean we've cracked reasoning and we've had the holy grail of reasoning and we're done and we can go home. No, because chain of thought prompting or reasoning has its own limitations as well. That's really important to discuss. The most important one is, as you just said, you cannot really trust chain of thought. You cannot really trust the trail. It's completely possible that it gives you a perfect trail, but wrong answer, or like the answer is correct, but the trail is completely gibberish. It's really possible. And for example, there is one of my favorite works where they train models to do natural language entailment. I'm hoping you guys know what entailment is. If not, then you basically give the model a premise or like a fact, and then you give it a hypothesis, and then you ask the model, does this follow the hypothesis? For example, in this example, it says the doctor visited the lawyer. That's the fact. And the hypothesis says the lawyer visited the doctors, which is not. So it is like the exact opposite of what the fact says. So in this case, the answer is non-entailment. That's why there's an N. And if you have some hypothesis that can be derived from the fact, then it is entailment. So they are training models to do natural language entailment on a set of tasks and on a set of sentences. It is completely possible that the model answers based on statistical heuristics or like based on pattern matching and produces a completely wrong COT to justify its choice. So maybe if you can read the caption, it says if a model is biased, then it would say it would predict all of these sentences to be entailments, even though half of them are non-entailments. And then, even when it predicts a non-entailment as an entailment, it would create a COT that would create a COT that's so good that it justifies why it took this decision, even though it's completely wrong. So the basic idea is that you cannot trust COT as a proof of explainability. And also another thing that you have to remember is that regardless of what you ask for it in the chain of thought, you have to remember that it's still an autoregressive process, and chain of thought is also created autoregressively. which means it's really possible that it can have hallucinations and problems like that. There are cases where you look at a chain of thought and it's inventing new people and inventing new rules of physics or like inventing new facts that don't exist. So if you don't know, if you're not aware of this specific topic that you're asking it about, you might think it's true and you might believe it, but that's why we should not trust the chain of thought blindly. And this whole concept of the result influencing the chain of thought is called post hoc reasoning. So instead of the model instead of the model using a chain of thought to find an answer, the model already decides that this is supposed to be the answer, and then it creates just some random chain of thought that would justify its thought, basically gaslighting us. It's called post hoc reasoning. And for example, this is another example from the same paper where they tried to train two different versions, where they tried to fine tune two different Claude 1.0 models. The first, and the task here is you give the model a fact or you give the model a sentence and you ask the model if it's possible or not possible. So, for example, if I say Mary went to school or something like that, it should say it's possible. And I saw pigs fly yesterday, then it should say it's impossible. And they fine-tuned two different models. One model was fine-tuned with a proper a data set that has equal amounts of possible examples and equal amount of impossible examples. And which is the one in the middle, the one that's highlighted in blue. And the other one on the right is a model that was trained with a biased data set, where where the entire data set was made of examples that were only impossible. So we know that when a data set is biased like that, the model would obviously, if a data set has never seen a specific target, it's really unlikely that the model would ever choose that target. It would always choose the target that it saw while they're training. And in this example, they asked it, some guy shot from outside the 18 yard line, and they're asking it if it's possible or impossible, and also doing zero shot here. In the unbiased context, it knows that this person is a soccer player and this term is a soccer term. And so it probably aligns and it's probably possible. In the biased context, where it only saw impossible examples, it's obviously going to say that whatever this is impossible. And then when you look at the COT trail, it says this person is a soccer player, but this term is not a soccer term at all, which is it's exactly contradicting itself. In one example, it said this is a soccer term, and in another example, it says it's not a soccer term. So it's going to all those extents to just justify its choice instead of just admitting that it's possible. And this is the whole concept of post hoc reasoning, where the reasoning looks completely coherent. If I don't watch football and I don't know what this is, I would probably think it's true. But if even though the trace looks completely coherent, it was constructed after the decision was made and not the other way around. And this goes about to imply that chain of thought has nothing to do with explainability. Just if you want to know why the model took a specific decision, you cannot just ask the model why it took the decision, because if the model took, I'll come to it. If the model was influenced by something else, it's probably going to use post-hoc reasoning to justify that. Yeah.
So we force the model to make like one shot decision, and then we force it to reason about this decision. But to keep the decision until the end, or can it change the decision it made during the chain of thoughts, reasoning afterwards?
If I understand correctly what you asked, it usually already makes a decision. Like it already made the decision if I'm going to say it's possible or impossible. In the middle case, it probably got influenced by the chain of thought. So it had the chain of thought and then it influenced the answer. But in the bias case, it already had the answer in its mind, because it only saw impossible examples, so it cannot think about anything other than the impossible examples. So it's probably going to say, even if you say like moon crashed or something, it's going to say it's impossible. Or if you say something that's really, really possible, it's going to say it's impossible. So it already knew that, and that influenced the chain of thought.
Positive examples are the decision you made or something else that you even.
I don't understand.
Like you said, positive examples for the bias case. Is that the example is the decision it made, or is it something else?
When I say positive, I mean when I say positive, I mean the plausible cases, and this only saw impossible cases. So Yeah, my answer. But maybe you can talk after the lecture. And someone else had a question? Yeah.
My question is similar, I think, but there's two different cases, right? So the bias context and unbiased context
Are completely different models.
And if we now look at the pre-computed example that that influences our later answer given to the user, right? What's the what is there any case in this where the reasoning happens after giving the answer to the user, or is this all part of generating the right answer for the user?
No, the reasoning doesn't happen after giving the answer. It always does the reasoning first, and I mean, it always shows the reasoning first before giving the answer. Like the order in which you see it in this example, in the red example, that's the order it prints it out. But when it's calculating, when it's doing the calculations, it already has in its mind that it's always going to be impossible. And then even before it starts printing it out, it's obviously going to print out that it's always impossible, and it tries to align the COT trail in a way that it makes sense to say it's impossible. I hope it makes sense.
Even if it's possible, it tries to make sense to it not being.
Exactly. So this term is completely even if you say Trump is a president of the United States or something like that, it's going to say it's impossible. Because it only saw impossible examples. I mean, it's not a proper model. It was trained on a biased data set that only had impossible examples. So even if you give it something that's completely possible, like mitochondria as a power of the cell or something like that, it's going to say it's impossible. And it's going to find a COT that makes sense, that would justify to say it's impossible.
Then what's the value to the user?
No, this is just to show, this was just an example to show, like it was not an actual model. Yeah, this was just to show to the user that that you cannot trust COT. Right. Any other questions? Okay, and you can let me know if I'm going too fast or if you want me to slow down. Good. Okay, thank you for that. And another important limitation of reasoning is that this is an example, this is an extension of what we saw previously. We know when a model is trained on a biased data set, it's possible that the model carries these biases like racial biases or religious biases or ethnical biases. You might have seen certain examples where an LLM gave like a completely racist answer or something like that. You cannot blame the LLM. It was the data that it was trained on. So if the model has all these biases are not fixed just because you're asking it for a chain of thought. So there is this example where they trained a model in this work, they trained a model to find if a person is eligible for a bank loan or something like that. In both of these cases, and they had like two different examples, and both of these examples had the same values, like the same credit score, the same age, the same income, and everything. But one of them said like this person is Christian, and the other one said this person is Hindu. And without changing any of the other variables that actually matter, if you want to find if someone's eligible for a bank loan, it said the person who's following a majority religion was rejected, and the person who's following a minority religion was accepted. So this was a bias that the model already had, and it's giving like perfect COT trails that would justify why it said that. It's an example. It's just an extension of the previous limitation. It just goes about to show that if a model already has a bias because of the data set, that bias is not going to be fixed just because you're asking it for COT. If it already has these biases, just because you're asking it for logical reasoning, it's not going to fix it automatically. And that's what this example says. If there are unverbalized biases, then the factors shift and the output appears very convincing, but it's not. And this type of oversight can be very unreliable, and these can go hand in hand. This is what I meant. There was another example in this paper where they had a story that included a white woman and a black man, and then they were giving a complete story of what each of them did, and then in the end they asked which one of these was probably selling drugs, and it said the black man was selling drugs, which is weird. And then they changed the story. Like the story was the same, but then they interchanged their names. So instead of saying the white woman did this and this, they changed the names and said it's the black man who did this and this. So we would assume that if you change the names, it should probably also change its answer. But it did not. Even in the next case, it said it was a black man who was selling drugs, and it was whatever it used to justify in the first case, it was completely denying itself and saying something completely different to justify its choice in the second case. So it just goes about to show that if a model has bias, it might use post hoc reasoning to justify its bias. So again, for the 50th time, you should not trust an LLM's reasoning trait. Yeah.
Is there a way to know and to guarantee a model not being biased?
That is a whole topic on itself. We can never say, I mean, unless if you are testing it, you would not find if the model is biased. You'll only find that the model is biased when you actually test it and put it to cases like these. And maybe, yes, if you have a specific curated data set that would, like this example, let's say, that is testing the model in like different settings. And if it changes its output, if it changes its output unfairly, you could probably say the model is biased.
So we can never falsify a model being biased.
What do you mean by falsify?
There's no way to say that a model 100% is never biased.
Yes, you can probably guess like it's probably biased, like giving it examples like these. If the model would change its answer in example like these,
I mean, the other way around. So I can not check a model to make sure it's not biased in any case, right?
yeah, the best you could do is like have a good data set and pray to God. I mean, it's not as simple as that. There are like, as I said, it's a whole topic on itself, and maybe you could discuss it after the lecture, or you could ask someone because he's probably going to give you a better answer than anything that I could say. Okay, any other questions? Okay. Yeah.
It's like the primary cause of this bias, is this like the imbalance in the data set?
Yes.
Other reasons been also added.
That's, I think, there might be other reasons as well, but that's one of the major causes that I know of. If your data set has, if the text corpus that you have has these biases, then it would probably also be reflected in the model as well. Any other questions? So let's go further. And so these are one of the main limitations, and the third one is kind of different. Is chain of thought even necessary? Do we actually need chain of thought in all of the cases? So this was a work, if you're looking at the image, this was a work done by Apple where they took two models, one thinking model, I mean one chain of thought model and one without. So for example, Claude Sonnet 3.7 was a thinking model and the other non-thinking version was used, and DeepSeek R1 versus DeepSeek version 3. So they were comparing these thinking and non-thinking models in a set of different tasks. The yellow graphs that you're seeing were easy tasks, the blue ones were kind of medium, and the red ones were really hard tasks. If you look closely, the non-thinking models were performing better than the thinking models in really easy tasks. And it was the other way around for medium tasks. So in like kind of medium complexity tasks, thinking was actually useful. But in really, really simple tasks, thinking was an overkill. Thinking was actually backfiring. Why is that case? Why is that the case? Because if something was really easy, then the model might have already gotten the right answer in the initial stages of the chain of thought, but then it still kept overthinking and exploring more variations that it ended up in something wrong. So, and what's more interesting is that when you look at some hard problems, both of them equally fail. So if you look at the red graphs, both of them are completely tanked. If a task is really hard, if a task is beyond a model's capabilities, chain of thought is not going to help it in any way. So the correct solution appears in that's what I said. In really easy tasks, the correct solution might appear in early stages of the chain of thought, but since it's not stopping there and since it's forcing itself to think a lot, it might end up in something wrong. So, to give you an example, I asked DeepSeek and ChatGPT what 27 plus 62 is, and DeepSeek thought for 1 second and gave the answer, which is 89, which the chain of thought followed how I would probably do a calculation. It said calculated the 60 plus 70 is 80, and 7 plus 2 is 9, and then it added. And what ChatGPT did is it also probably had a chain of thought trail in the background that we cannot see in the UI. In This is just an assumption. Obviously, I cannot see it, but the assumption is that it in its chain of thought, it knew that this task is a mathematical task. So we could actually call the tools that we have, like Marina just talked about. It called a calculator tool and it took it out of its pocket and used it instead of trying to verbally calculate it. And in cases like these, COT might actually be an overkill because you don't have to think for like 10 seconds for something that's really simple. You can just use a tool. And also, something else that you have to keep in mind is that most of these vendor models like ChatGPT or Claude or DeepSeek, they have COT baked in, even if you cannot see it in the UI. And now one of the examples that I had the most fun while making this PPT, credit goes to Simone, by the way. If you ask DeepSeek, which is a thinking model, that I have juice in my fridge, and is there something that I can drink because I'm thirsty? It thought for like 5 whole seconds and then said yes, which is completely insane because maybe that's a personal opinion, but it's insane that it has to think for 5 seconds for something that's so trivial for us. Like if I were to ask you if I have something in the fridge, you don't even have to do the calculation in your mind. Like, yeah, juice is drinkable, juice is in the fridge, so that applies. There's something drinkable in the fridge. We don't have to do that. But something that's so innately embedded in the way our brains are hardwired, LLM has to think about it for so long in order to get this done. So the question is, obviously we can see that it's an overkill. COT is an overkill in this case, but does it mean that DeepSeek is dumb? Does it mean the model is dumb? Or it's like, it's useless? I'll come to that when I finish it. Does it mean that the model is dumb? It's not the case because if you look into the reasoning trail and look at what it was thinking if this is a logical puzzle. Is there a trap in this question? So so what it did is instead of just giving an answer from the top of his head, it was definitely overthinking it, but it was overthinking it in the right way. It was thinking if there is a logical trap in this question that I have to avoid, because if it doesn't catch that trap, it's probably going to give you a really embarrassing answer. So it's true that as we saw on the previous graph, that in really simple cases, COT might be an overkill, but that there is a reason why we just don't turn off COT. Because in certain cases where the task looks really simple, but it has some logical trap behind it, we need COT and we need that extra overthinking in order to get out of it. And with that, we end reasoning and COT and question. Okay.
Yeah, about the last one.
Mhm.
I mean, I would also be part of this, somebody has transmitted their choose and then they accidentally have something different. So like, it's not like I would like it's a puzzling question. But
I mean, okay, maybe this is a wrong example. Okay, maybe it's on me. This is a wrong example to actually say that. But if I were to ask you something else that's really simple, like what's 2 plus 2 or something like that, you could ask DeepSeek what's 2 plus 2. It would still think for like 2 seconds. This was just an example that me and Simon had on the top of our head. But you could ask the uh, crux is you could ask it something really simple where it does not need logical reasoning, but it's still employing it. Is it good? Is it bad? It might be bad in a sense that it's an overkill, but it's also good in a sense that it's avoiding a potential logical trap. Yeah. So any other questions? Cool. So uh, and please let me know if you guys would like a 5 minute break. And if not, we would get into the last topic for today, which is really exciting, how we can efficiently train, fine tune, and infer from these large language models. All of the things, we saw a lot of things today, and also in our previous lectures, we saw how LLMs work, how to infer from them, how to fine tune them, how to do alignment and reinforcement learning, how to use COT, everything that we learned for all of these days, it follows one simple assumption. The assumption is that you can actually run these models. What if you cannot even run them? What's the point of learning all of these? And it might be stupid because we are running it all the time, but it's not as easy as we think because it's in the name. These are really large language models. They are massive. And it would take a lot of data to even load these models and to give you an example. Imagine GPT-3 175 billion parameter model, which is kind of well known, I would say. And it uses 32-bit floating point numbers, which means every weight parameter is stored in a data type that takes 32 bits. And if you were to calculate 32 bits, which means like 4 bytes, if you were to calculate how much data you would need, it's you multiply the number of parameters by the size of each parameter, so 75 billion times 4 bytes, that would be 700 GB, just the size of the model. If you just want to load the model into your computer, you need like 700 GBs. Even if you had like the best laptop that I know of, you would still need at least like 9 or 10 of them, because you could have like a top research GPU that might have 80 GB space, but you still need a lot of, you still need like more than 5 to 10 of these working parallelly just to load the model. But if you've ever taken some NLP course, or if you've done any homework, you might have seen that we are also importing these models in Google Colab and running it in Colab. How is it possible? Like, you cannot, even a whole laptop is not, even one whole laptop is not enough, but we are just importing it in like one Google Colab notebook. How is it happening? And if it's so massive to even load the memory, let alone to run it, how are we doing it so easily? The answer lies in the fact that we are optimizing every single step in the LLM process, like we in training or fine tuning and inferring, we are doing massive optimizations that it makes it possible to load these and possible to train these without the overhead that we could imagine. So, one important optimization that we need to do is while training, because training is insane. We have such a massive model, and we might have to train it for several epochs, like sometimes even thousands of epochs. Imagine training a model that's this big, and there are a lot of things that goes inside training. There's the optimization states, and there are a lot of different things that goes inside. So you need more data than just the model size itself. If the model size was like 700 GB, you need much more data to train it. I don't mean the data set, but like extra the optimization states that you have to store, and like the intermediate logits. Like you need more data to train the model than the data size itself. And the problem, and we there is one solution to that, is that we use FP32 bit numbers. So as we know, FP32 bits take like 32 bits storage space to store each number, which means it has a really huge range, and it was also really precise. You can store like really precise numbers, like I think like 10 or 15 10 or 15 digits after the decimal point. But the problem is it's so big, so it makes it expensive to do the calculations in such huge numbers with such precision. But it's also stable, and this is what we would prefer weights to be. But it's still expensive. So what do we do about that? One option could be to use FP16 numbers. So instead of using, it's also a floating point number, but instead of using 32 bits, we are using 16 bits. It would have a much smaller range, but it's faster. Why don't we just use that? It's probably like twice as fast because it uses only half the memory. But the problem is FP16 does not have the same range as FP32. So it cannot hold numbers it cannot hold like really microscopic numbers that FP32 can. So in this example, they trained a multi-box SSC detector network. You don't have to know what that is. Even I don't know what that is. But they just tried to show the weights of the model. I mean, not the weights, the gradients of the model, and they showed that most of the model's weights are in the range of like 2 power minus 27, 2 power minus 28, in that range. If you could see the red line in the graph, that's the limit of FP16. Anything to the left of the red line cannot be stored by FP16. Anything to the right can be. But if you can see, anything to the left of the red line would be just rounded off to 0 if you're using FP16. But you cannot do that because majority of the gradients are in that space. So if you were to use FP16, majority of the gradients that you get while backpropagating, they would just be rounded off to 0. So you get like a gradient. So there is instability in training, which is called gradient underflow, when your data type is not precise enough to store the numbers. So everything is rounded off to either the minimum value or the maximum value, which is introducing instability in your training. This is the problem with FP16 because it leads to gradient underflow. So FP32 is precise, but it's really slow. FP16 is fast, but it's not precise enough. So what can we do about it? We can, one possible solution is that we use FP16 for doing the calculations, but FP32 for storing the weights. Instead of just using one specific data type throughout the training process, we change the data types in between, and we're using the smaller ones where speed matters and the bigger ones where precision matters. That is called mixed precision training. So not using the same data type throughout, but changing the data types and changing the numbers. So the three-part solution was from the original paper that introduced mixed precision training, so I had to include it. But this is the basic idea. If you were to look at the illustration, you have FP32 weights, which are first converted to FP16, and then we do the forward pass, backward pass, and then the backward weights. And then before the weight updation is done, we convert this FP16 back to FP32, and then we do the weight updation in FP32. So all of these, the green line would represent when the numbers are in FP16 space, and the red line would represent when the numbers are in FP32 space. So we are interchanging them in between training. So you don't lose that much information, but you're gaining a lot of speed. That was the first part. And the second part is, as I said, you have the weights needs to be precise. So they have a FP32 master copy of the weights that they're not changing. So instead of having an FP16 weight matrix, they have an FP32 weight matrix, and they're only changing the FP32 weight matrix. Is it a mouthful? Like, any doubts? Everybody understood? I don't believe that. Okay, I have to believe you. And the last thing is something called loss scaling. So if you were to see the previous example, we saw that most of the gradients were below the specific range of FP16. So even when you're changing it to FP16, something that's in the range of 2 power 27, 2 power minus 27 would obviously go to zero. How can we bring these gradients into the range of FP16? By just multiplying with a constant. If you were to multiply the gradients with something like 8, let's say, which is 2 power 3, if you're multiplying it with a scalar 2 power 3, then you're increasing the powers of all the gradients by 3. So something that's like some gradient in the range of 2 power minus 27 will come inside the range of 2 power minus 24 because you're adding 3. So now it's inside the range of FP16. And before you do the weight updation, you divide it back. So you're not affecting the model's training. This is called loss scaling. It is good, but you're adding an extra hyperparameter that you have to train. 8 is just an example that they used in the previous, 8 was just an example that they used in this graph, but the actual scalar that you have to multiply your gradients with might differ depending on what task you're doing, depending on what your training objective is. So it is an extra hyperparameter that you have to tune. But the result is there is not much of a significant accuracy loss per se, but the training is massively, the training speed is massively increased. Another alternative to that, instead of using FP16 in the training process, instead of alternating between FP32 and FP16, we can alternate between FP32 and bfloat 16 or bf16. This is another type of data. This is another data type where it has less precision, but it has the same range as FP32. So I am really sure you don't understand what I mean. If you could see the illustration, any number that you have to represent in a floating point space will be converted in this form where there's a sign, and the number is converted to 10 power the exponent form, and there's only one decimal place to the left and there are multiple decimal places to the right. So any number is converted to this format, and then the mantissa is in, let's say if you're taking FP32, the mantissa is stored in, like, there are 23 bits to store the mantissa, and there are only 8 bits to store the exponent value. And the base is 10, so base is always 10, so you don't have to store it at all. So FP32 takes 23 bits FP32 takes like 23 bits for Mantis alone, so you can store a lot of digits after the decimal point. But if you were to take FP16, it has only 10 bits, so you cannot store a lot of decimal points after. I mean, you cannot store a lot of digits after the decimal point, but the memory size that you need is reduced. BF16, on the other hand, has the same amount of exponent bits. I don't know why this is happening. Has the same amount of exponent bits as FP32, so it also has 8 bits, but it just reduces the mantisar. So you cannot store a lot of digits after the decimal place, but the exponent here, the blue one, it's the same as FP32. So why do we have to do all of this and why go through all of this? Because if you're using FP16, it's having the same memory space as if you're using BF16, it's having the same memory space as FP16, but the range is same as FP32. It might be confusing, but if you look at the table here, FP32 has a range from 3 power has a range from 10 power 38 to 10 power minus 38. FP16 has only a range from 10 power 4 to 10 power minus 5. But BF16 also has the same range as FP32, even though it's having half of the size. So why substitute this with that? Because if you were to use BF16, everything is in the same range as FP16, so you don't have to do loss scaling. So you don't have to worry about a specific value being rounded off to 0. So one less hyperparameter, so good for us. It's now it's so popular that now most of the vendor models like Llama, Gemini, everything is using everything that's using empty mixed precision training are alternating between FP32 and BF16 instead of FP16. So any doubts? Should I believe that everybody understood? I'm going to believe you guys. So we saw how we can optimize while training. Now comes influence. You've trained the model completely, you've done everything, but now you have to infer from it. You have to like put the model to actual use. It is still a huge task because it's still a huge model and you have to run the model at least like you have to at least do like one forward pass to get the output. It is still not a child's play. It is still a huge task that we have to do. And as we said, the model size can be really big. But one advantage is that it's not going to take that amount of memory as it took for training because most of the model is just frozen. You're just running it through once. So, and also another thing that we can take advantage of is that we don't need the weights to be that precise when we are inferring. Because imagine if the weights are so precise and if you're using the actual weights, you get the actual probabilities for the next word, and then you have the probability ranking, and then we are choosing the top word and we go home. But we don't actually need the actual probabilities at all. We only need the ranking of the models. So even if the probabilities are somehow slightly rounded off, the ranking is still going to be the same. I mean, you cannot massively round off like everything to like 2 decimal places and expect the probability to be the same. But if you were to do a little bit of rounding off, the probability might not it might not affect the rankings that much. So if that's the case, we can actually make use of that. Imagine you were an architect or something like that, where you had to calculate all the different force vectors in all different directions. And in a case like that, you cannot really afford to round off something because that could mean the difference between life and death of your customers, and where your bridge collapses and you go to jail. But or something if you were an astrophysicist where you had to decide in which direction or which angle I need to launch the rocket, even if it was off by like a really minute, even if the precision was off by a small amount, you might completely launch it to a different planet and again go to jail. So in cases like these, precision actually matters so much, but for us it doesn't. I mean, don't get me wrong, it does matter. You cannot, as I said, massively round off things. Like for example, if you had like 32-bit, you cannot round off it to like 4 bits. That's massive. Then you probably have a parrot that's talking gibberish. Your model is completely useless now. But you could afford to do a little bit of rounding off without losing much of the accuracy. And we can take advantage of this. And that is called quantization. You might have done it in your life, you might have heard about it, but it's my duty to still talk about it. So if you were to look at this graph, this is the this is the histogram of all the weights from BERT base case model. And you could see that 97% of all the weights, 97% of like all the different weights are centering between and centering around zero, and they lie within the range minus 0.1 to plus 0.1. But we know the massive range of FP32. FP32 can store from like 10 power minus 10 power 38 to something like that. We don't need such high precision because, I mean, we don't need such huge range because we know that the weights are going to be clustered around a single point, like maybe clustered around zero, and they're not that varied yet. So we don't need that big of a range. So we could take use of this. We can make use of this. So quantization refers to a technique of performing all the calculations. Instead of in the original space, we are converting them into a smaller subspace, like for example, converting the floating point numbers into an integer number and then doing the calculations. So we are obviously losing some precision. Yeah, obviously it's not this, you're not getting the same probabilities of as using a floating point number, but the rankings are more or less the same. So we can afford to do this. So, as I said, most of the models weight are clustered around zero. So the full range of FP32 is rarely used. So quantization can be used to map FP32 to something smaller like integers. The trade-off is that quantization is always lossy. If you were to quantize a weight tensor while calculating, let's say, you will never get the original tensor back. We will see an example to show what I mean. And that's the reason why you cannot do like 4 bytes to 4 bits quantization. Then, as I said, you just have a parrot that's talking gibberish. So there are a lot of different varieties of quantization. You don't need to know exactly like everything, but two really important linear quantization techniques are symmetric quantization and asymmetric quantization. Symmetric quantization is used when the target, like you have the original range and then you have the target range. Symmetric quantization is used when the target range is centered at zero. So it's like, let's say from plus 100 to minus 100 or something like that. In this quantization, zero from the original range is mapped directly to zero in the target range. Whereas asymmetric quantization could be could go from any random range from minus 50 to plus 100 or something like that, where zero is not the middle part. So in asymmetric quantization, the zero in the original range will not exactly map to zero in the target range because zero is not the center point anymore. That is more or less all you need. You cannot, asymmetric quantization is kind of more, is kind of having a more overhead because of the formula and everything and more things that you have to store. But it works better for cases where the target range is not centered around zero. So this is just an example. You don't need to know how to do the calculations or anything in terms of the exam, but it's included to show you something really important. So if imagine this weight matrix is the weight tensor that you are using while inferring, and from FP32 bits, we are converting it into signed integer from minus 127 to plus 127, which is centered around zero. So you can use symmetric quantization for this. So the form, don't ask me where the formulas came from. It was from the original work of quantization, the white paper for quantization, but they explain like how they came about with this formula and everything. It's not relevant for us, but you just need to know how, you just need to know something else. So you use the formula and then you store the scaling factor. And then to get a quantized matrix, you divide the whole weight matrix with the scaling factor and then you round it off. So this whole floating point tensor has been converted to integer tensor now. And imagine instead of storing 9 floating point numbers, which would be 4 bytes per number, so 9 times 4 is 36 bytes. Instead of storing 36 bytes, you're only storing 9 integer numbers, where each number is like 1 byte. And then you have to store the scaling factor as well, which is like 1 extra floating point numbers. So instead of storing 36 bytes, you only have to store like 13 bytes, which is like 2/3 of reduction, like 65% reduction or something like that, which is massive. And if it's like a two-thirds part reduction for something this small, imagine how much the reduction would be for a really huge tensor. The main purpose of this slide is to show you the bolded numbers, When you dequantize it, that is like instead of dividing, you multiply the quantized matrix with the scaling factor, you don't get exactly the same numbers as we started. So that goes about to show that quantization is lossy and you'll not get the same numbers back. And I swear I'll finish in a couple more slides. Please bear with me. And this is also not relevant for the exam, but it's relevant for the next homework 3, which is another method to optimize while inferring, which is called KV caching. I want everyone to recall how transformer works. For every token that we have to find, the target token is it's attending to every previous token. So we have the query matrix of the target token. We're multiplying with the key matrix of every other token that we already saw, and then we're using the value matrix of those while doing the softmax and everything. I hope you know. We know that we are using the key and value for we are using the key and value matrices of all the tokens that we already calculated. And each time we are predicting a new token, the key and value matrices are calculated again and again. This is one of the reasons why transformer has a complexity of O of n squared, because you're calculating key and value again and again. But it's not changing anymore. So why do you have to calculate it? Why do you have to calculate it to for every single token? We can just cache it. And that's what KV caching does. Instead of calculating the key and value matrices each time, we calculate once and then we cache it in main memory. When you do that, the complexity of transformers reduces massively from O of n squared to linear complexity per step. Of course, it's not like complete linear because you have a lot of layers and everything, but you get the idea. We try to do this every time, but the problem is that when you cache things, you have to cache it in the main memory. But if you have a really massive context size, or like if you have a lot of layers, or the hidden dimension is too big, then you have a lot of things to cache, and you might not have enough capacity in your main memory to cache all of these things. This is the one important drawback of KV caching. Of course, there are a lot of advanced techniques where we know that when you don't have enough space in the main memory, you have to put things in the disk memory, and then so you have to have like an eviction strategy and like which one needs to be evicted. So we have a lot of cache eviction strategies that are new modern flavors, or we also have compression strategies where instead of storing the whole matrices, we compress them into something small. And so there are a lot of different KV caching has one drawback of taking a lot of memory space, but we do also have a lot of different flavors that are trying to combat this. This is all we need to know about this, right? Any questions?
Make sure I understand. You can only do that at the first layer of a transformer, right? Because, I mean, when you go farther on, then you're gonna use these matrices for the attention on the regulated presentations that you build, which depend on the whole suite.
Yeah, so yes, it's true. And the caching happens for every different layer separately. So you're not caching the same thing for the entire model, but it happens separately, and that's why the O of n, that's why the O of n, I mean, that's why the O of one complexity, the linear complexity is per one step instead of like saying the whole transform is running at linear complexity.
You can only cache for the embedding that you have in your embedding matrix. You can compute the query and embed the key and value, but you cannot do it further deep to the network because then it's not your embedding matrix anymore, but that depends on the whole system. Each representation is contextualized, so it depends on the whole system. It's not on the token itself.
Yes, that is true, and I think Simone would be able to give a better answer than me. And please write us on Discord where I could ask him and get back to you. Okay. Any other questions?
So,
yeah,
is the complexity linear or constant? Because O of one is constant, right?
Yeah, I'm sorry. It was my fault. O of one is constant complexity, but also it's not constant for the entire. It's not constant for like the entire transformer model because this is only for one step, and you have like a lot of steps. So yeah. It's O of one is constant, non-linear.
Yeah.
Anything else? And thanks for pointing that out. Anything else? Okay, so this is with optimizing while inferring. And then comes the final part, optimizing while fine-tuning. as I already said, when you're fine tuning, you have to have all of these extra states like the optimization states, and the optimizer will take different the optimizer has to store like different values for each and every weight parameter to know how to optimize it. So if the model size is 700 GB, then when you fine tune it, you need like twice the amount of data for twice the amount of data as the model would actually take up. So this is still a huge problem. So you cannot afford to change, you cannot afford to touch like every single parameter of the model. You can, we obviously can, we are doing that, but it's so expensive. So what we can do is instead of training all the parameters, instead of retraining all the parameters and updating everything, we only try to update a specific set of parameters and still somehow getting the same accuracy. So there are two important ways of doing that, which I'm sure you might have heard at some point in your life, which are adapters and LoRa fine tuning. Obviously, there are so many other variations as well, like adapter fusion and like prompt-based techniques, but these are the most, these are the focus for today. So, what are adapters for if you are not aware of them? Adapters are just mini MLP layers, mini multi-layer person product layers that you are injecting within the transformer layers. So you could see the left illustration is an actual transformer block. Then it's a real transformer layer. It has like multi-layer tension, feed-forward network. And before the skip connection is happening, we are injecting an adapter layer. This adapter would also have like a feed-forward layer, non-linearity, and another feed-forward layer. So so we are injecting these adapters in the middle of the transformer layers, and we freeze the rest of the transformer. Only the adapters are not frozen. So when we are fine tuning with a curated data set, like the small data set, we don't touch any of the actual transformer parameters, but we are only touching the adapter parameters. And the adapter parameters would change and shift in a way that they change and shift in a way that when you finally test it, it performs in a way as if the whole model was fine-tuned, as if as all of the parameters were touched. So if you look at the design, there are a couple of important, like there are four important things. One is a down projection. So like this box that you see is the actual size of the logits that are coming from the adapter layer. I mean, that are coming from the transformer layer. The adapter is using a down project feed-forward network to kind of project it into a smaller space. So if the original logit was like I don't know, if the original logit tensor was like 100 elements long, then you could down project it into something really small, like 8 or 10. And then you're doing the non-linearity in the smaller space, and then we are up projecting it back to like 100 or something. So we can pass it back to the transformer layer. So, and then there's another important thing, which is the skip connection. It is possible that when you're fine tuning, not everything has to be fine tuned. Like it's possible that maybe this attention head in this transformer block does not have to change, because we know like every attention head, like every transformer block is it's doing something, and maybe it's possible that this specific transformer head does not have to change. So in that case, this adapter there is just useless, so it's not going to learn anything. That adapter is just going to be zero. So for that case, for those cases, we also have the skip connection in the adapter's biology. So if the adapter is not learning anything, then the input is just passed as the output. So this is just for safe initialization. That's just the basics of how skip connections work. Any doubts? Or should I like say it again? Cool. So So the adapter size here, M, is really important because it determines how many parameters we end up training. So if the hyperparameter M is really large, then when we've down projected, we still have a vector that's really huge and lives in a higher dimensional place. So we end up training more parameters. And if M is less, then this vector would be really small, and throughout the model, we end up training lesser parameters. So this should be taken with a grain of salt, because if we reduce the size m really by a lot, then the model might not have enough parameters to even fine tune correctly. So that might cost us in performance. But the advantage is, since we are training a smaller number of parameters in comparison to the whole model, the training would take much less time than training the whole model. If you see the table on the right, uh, in this work, they trained a birth baseline. They tried to fine tune the birth baseline model on a couple of a lot of these tasks. And when you look at the average, the completely fine tuned model has an accuracy of 73.7, but the adapter fine tuned version has an accuracy of 73.3. Even though it's slightly less, when you look at the number of parameters that was trained per task, then the completely fine-tuned model has 100%, because obviously all the parameters were trained, all the parameters were fine-tuned. But when the in the adapter's case, only 1.14% of the total parameters were retrained. So that's a massive improvement, because we're only training less than 2% of the parameters, but getting comparable results to a completely fine-tuned model. And that goes about to show how powerful adapters are and why they've been so widely used in research and in vendor companies. The other parameter efficient fine-tune technique is low rank adaptation, or LoRa. I hope everybody remembers how the weight updation works in deep learning. We have the original weight, so the new weight is equal to the original weight plus the change in weight term, and the change in weight term is the input times the learning rate times the loss gradient factor. So if you have a huge weight matrix, like a 100 by 100 weight matrix with 10,000 weights, then the updation could be imagined as the new weight updated matrix is equal to the old matrix plus the change in weight matrix. Problem is, the change in weight matrix del W is of the same size as the original matrix. So we have a lot of parameters to touch upon, a lot of parameters to work with. What if this change in weight matrix can be approximated as a product of much smaller matrices without much loss in accuracy, but the sum of all the parameters in these two matrices are less than the parameters in the total weight del W matrix. This is the whole idea of low rank adaptation. It has been hypothesized or proved it has been hypothesized that the del W matrix always has a much lower rank. And just a quick recap on what rank of a matrix is the total number of linearly independent rows or columns that a matrix has. We see it with an example in the next slide. So in here, the weight updation works like this. Instead of the actual weight matrix plus the del W matrix, we decompose the del W matrix into two different matrices and approximate del W as a product of these two matrices. And these two matrices, B and A, are much smaller than the original matrix, because the original matrix is of size D times K, but B and A are of sizes D times R and R times K, where R is very small than both D and K. You could also see it in this illustration, even though it shows it's from the original low rank adaptation paper, even though the illustration says it's A times B, but it's just notation. The whole idea is that we decompose the del W matrix, the updation of weights matrices, into a product of two different matrices, and these matrices are much smaller than the original one. So the original weights, the blue box here, the original weights are completely frozen, and only B and A matrices are trained and updated. We see it in practice. For example, consider this to be the weight tensor of this to be the weight tensor, and it is of size t times 3, which means it has 9 total elements. But if you notice, the second row, the first row is the second row times 2, and the third row is the second row times 3. So all these rows are linearly dependent with each other. If you just know the second row, you can reconstruct the first and third row in with just the second row. So these rows are linearly dependent, and since you only need one row here, the rank of this matrix is one. Even though it's more complicated than that, I'm giving you a gross explanation. So you can decompose this matrix into two smaller matrices of size 3 times 1 and 1 times 3 because the rank of the matrix is 1. And when you multiply these two matrices, you get the original matrix back. But the thing is, both of these matrices only have 3 elements each, and when you combine them, you get a total of 6 elements. But the original matrix had a total of 9 elements. That is a 33% reduction in size. Imagine a really huge matrix like a 1,000 by 1,000 uh, weight matrix, and it has a very small rank. Then we save up a lot of space by decomposing them. This is the whole idea of LoRa. And if you look at the results, uh, in the original LoRa adaptation, LoRank adaptation paper, they trained the GPT-3 model, and the completely fine-tuned model has an accuracy of 73.8, but the LoRa fine-tuned model has an accuracy of 74, which is actually slightly more than the completely fine-tuned model. Imagine getting more or comparable or even better results by only training a fraction of the parameters. So in this case, we are only training like 4.7 or 37.7 million parameters, but the original model has like 175 billion parameters. And the authors of the original low rank adaptation paper report that ranks of 1, 2, 4, or 8 are sufficient for most of the NLP tasks, and they are now widely used values for the parameter R. And with that, we come to the last part of the lecture, which is grokking. I hope everyone is aware of at least the term grokking because it was really famous in social media a while ago. Imagine you are training a model for something and the graph kind of looks like this. The training accuracy goes high, but the validation accuracy is still so low and it's almost close to zero. It is a classic case of the model overfitting, and most of us would stop training at s- somewhere here. What if you don't stop training and you continue training the model? It is possible that after a really high number of epochs, the model just suddenly learns how to generalize, and the generalization ability goes really high. The validation accuracy goes really high, it skyrockets, and this change is so abrupt and not a gradual change. This concept is called grokking. It's it's the idea that neural networks can learn how to generalize even well past the overfitting stage. So initially, the model just memorizes the training data and there's zero validation accuracy, but then with continued training, the validation accuracy jumps to 100% abruptly. There are a lot of hypotheses on why grokking works and how it works. We're not getting into the depths of that in this lecture, but it's really interesting, and I would suggest everyone to like look it up. But weight decaying and the one hypothesis is the weight decaying and the cross entropy laws play a really big role. Just a fun fact, the word grokking first appeared in a science fiction novel named Strangers in a Strange Land, where it meant to drink something, but throughout the course of the book, it turns into understanding something so profoundly all of a sudden that you become what you understand, and what you understand becomes a part of you. And the lore is that researchers in OpenAI were training a transformer model on some task and they forgot to turn off the training and they went on vacation. And by the time they came back after 3 or 4 weeks later, they found that the model has been training the whole while. And when they stopped it and checked the graph looked something like this. It looked like it was overfitting at some point, and then all of a sudden, with like around 10 power 5 epochs, it suddenly learned how to generalize better. So if grokking would boost generalization, why don't we just always do grokking? Like everybody could just set a really high number of epoch and train for a large number of epochs. Why don't we just always do that? The main reason why we don't do that is that we don't know when it will happen, and even if it will happen, we cannot guarantee it. It's in the original paper, it's said that the the lesser the training data you have, the longer it might take for a model to grok. And this time grows rapidly as the data set gets smaller. So if we don't have a data set that's big enough, it's at a point it's even pointless to think about grokking. And also another reason is because it's so expensive. Huge vendor companies, like huge companies, can afford to do grokking because they have the resources for that, but normal researchers or universities cannot afford to do it. And another important reason is grokking is very sensitive to all the hyperparameters, especially the learning rate, which has to be tuned in a very specific way that if it's slightly off, grokking might just never happen. And it's also possible that grokking just never happens on real world tasks. The researchers in OpenAI were actually training a set of transformers on some mathematical, like arithmetic tasks. But grokking might not happen because in real world examples, because real world tasks and scenarios are much, much more complicated than just training transformers on arithmetic tasks. So uh, it is it is customary that a lot of these vendor models try to do grokking because they have the resources, but we don't usually do it. And with that, we come to the end of this lecture. Today, we saw how instruction tuning works and how it can improve the LLM's ability to perform on tasks that it has not seen before, and how we can use reinforcement learning to improve the model's behavior and align the model's behavior to better resonate with humans' preferences. And we saw how we can extend an LLM's abilities using retrieval or API calls and how we can incorporate tools in them. We saw how to induce reasoning in LLMs by a chain of thought prompting. And we also saw how we can incorporate several optimization strategies to make it practical to run and infer from these models and why these strategies are really important. With that, we come to the end of this lecture. Thank you so much and probably see you next week.